Hello everyone, welcome to this lesson. So this lesson we're gonna discuss our last topic in curve fitting, and that topic is called interpolation. Now in the previous lessons we dealt with regression analysis, right? If I have a set of data points, you can fit a model that describes all the data points using regression analysis. And we went through linear regression, a first order polynomial. We also went through polynomial regression and give an example of a second order polynomial. And we also went through other types of regression analysis through complex equations like logarithms and power by the concept called linearization. Right? So in this lesson, we're going to go through interpolation. And the main difference between regression analysis and interpolation is with regression analysis, you're fitting one equation or one model to all the set of data points. But in interpolation, sometimes you're actually interested in a point, right? A value between two of your data points. And what interpolation does, it takes those two data points and it creates an equation between those data points. And we use that equation to get that value that you're interested in. And what I mean by that is, this is a set of data of the change of temperature with depth. And say, for instance, I am interested in what is the temperature at a depth of 16, and depth of 16, that's between this data point 14.2 and this data point 19. So what interpolation would do, it would create a equation between those two data points to get me what is my temperature at a depth of 16. Okay, so if you look at this graph, I have 10 data points, and those 10 data points will create basically 9 intervals, which means I can describe this entire intervals using 9 equations as you see here. And what we're going to do in this lesson is cubic spline, which means basically we're taking a third order polynomial to describe each one of those intervals. Now I want you to look at each one of those equations. To describe a third order polynomial, we need 4 constants, right? We need A, B, C, and D. And since we have 9 intervals to describe all these data points using those 9 equations, I need to find those 36 unknowns, right? Because each equation has 4 unknowns. So which means if I have 36 unknowns, I need to have 36 equations to use to find those 36 unknowns. Now, we're going to go through what are the 36 unknowns, but we're not going to go and use this technique. I want you to be aware of this technique, but we're going to go through a much simpler technique. So one of the equations that we can use to get those 36 unknowns is we're going to say that the function values must be equal at the interior knots. So that's one of the conditions that we're going to be using. So at each knot here, so we have 8 knots, we're going to have 2 equations. So now we have 16 of the equations that we're going to use to get those 36 unknowns. We're going to say that the first and last function must pass through the endpoints. So the first function here that we have must pass through this endpoint and this endpoint. So we have 2 other conditions or 2 other equations. So we're up to 18 functions. So also the first derivative at the interior knots must be equal. And what that means is that the first derivative using this equation and the first derivative using this equation must give the same value of the first derivative at that knot. So that would create, since we have 8 knots, that would create 8 more equations, right? So we have 18, and 8. That would give us 26 equations, right? So 26 equations, so we have 10 more equations left to find. So another condition is that the second derivative at the interior knots must be equal. So much like the first derivative has to be equal, the second derivative also has to be equal. So we have 8 more conditions. So now we're up to 34. So we have 34 equations to get the 36 unknowns. So we have 2 more conditions left, or 2 more equations to develop. Well, the last condition is that the second derivative at the end knots has to be 0. So the second derivative here is 0, and the second derivative here is 0. So we have now a total of 36 equations, or 36 conditions, to get those 36 unknowns. Massive amounts of equations. So this is not the route that we're going to be using, but I want you to be aware of that route, that we're actually fitting a cubic polynomial to each one of those intervals, and the cubic polynomial has 4 unknowns, and since we have 9, we have 36 unknowns, and those are the conditions that have to be met when we're actually finding those 36 unknowns. Now, there's an alternative technique that defines each one of those equations, not in terms of A, B, C, and D, but in terms of the second derivative. So this interval will be defined only in terms of the second derivative at the start of the interval and the second derivative at the end of the interval, right? So if I want to create an equation describing an interval, I only need to know what the second derivative is at the start and the second derivative at the end, right? So you would assume, right? You would assume each interval needs those 2 pieces of information. So we have 9 intervals. I have those 2 unknowns. That means I would have 18 unknowns. But that's not what we have here. We have 8 interior points, right? So if I get the second derivative at each of the 8 interior points, and I know that the second derivative at the end knots is equal to 0, that means I have all the information I need to create the equations, right? Because for each interval, if I have all 8 of the second derivatives, I have the information at the start and end of the interval for all the intervals, right? So we went from needing 36 equations that we have here to only 8 equations, right? Or 8 unknowns, which is the second derivative at each of the interior points. Keeping in mind that the second derivative at the end knots is 0, okay? So we end up with this generalized equation that I have here. So I can take this generalized equation here, and basically xi and xi minus 1 are basically the start and end of the interval. And here, basically, the second derivative at xi minus 1 is the start of the interval. The second derivative at xi is the end of the interval. So you can see all of this is defined in terms of the second derivative in the start and the end of the interval. I also want you to see that here we have an x, that it has no I or I minus 1, because that's the point that I'm interested in. That's the point that I want to get that I'm interpolating for, okay? Now I'm going to rewrite this equation, and I'm going to rewrite it in terms of the form that you have down here. Now this is a general form that if I actually evaluated at I equal 1, I equal 2, I equal 3, 4, 5, and I is basically telling me the node, right? So I equal 1 is node 1, I equal 2 is node 2. When we do this, we create this matrix that I have here, right? This is a special type of matrix that I've described before. This is a tridiagonal matrix, okay? Now, in developing this matrix, you see this coefficient at the beginning here. This coefficient is going to be called E. This coefficient here in the middle is going to be called F, and this coefficient here, we're just going to call it G. And everything on the right-hand side here, we're going to call R, okay? And you can see that F, E, and G are all defined in terms of the x's of the data points that we have. So we can get all of the F, E, and G right now, right? And the R is defined in terms of the function values at the x's, right? At the function values here, the temperatures that we have here. So we can also calculate all of the R's. So if I can get all of the E, F, and G, which means I have the matrix A here, and I have all the R's, basically I have all the information I need to get all those solutions, right? The second derivative at the first node all the way to the second derivative at the 8th node, right? And now I have all the information that I need to create all the 9 equations for all the 9 intervals that I have. Okay, so given that we're done with describing the theory, how about we actually go in and see how does this would translate in terms of the code? Okay, so kind of to like recap briefly what we're doing here. The difference between interpolating and regression analysis. The regression analysis would take all the data points and it would fit only one model to it, right? What interpolation does is going to fit a model or an equation to each one of the intervals. Here we have 10 points, so we have 9 intervals, and we fit an equation to each one of them, a cubic equation to be exact. We said if we went with the conventional normal way of finding this, a cubic has 4 unknowns, right? We have 9 equations, so 36 unknowns. And we found those 36 equations or conditions to get this. And this is not the route that we chose to take. We took an alternative route that instead of dealing in terms of A, B, and C, it deals with the second derivative. The second derivative at the start of the interval and the end of the interval. And we found that we only need to get the second derivative at the internal nodes, and we have all the information that we need, right? And this is the equation that would define each of these equations in that second derivative form. By rewriting this, we have this general form in terms of I, and by writing for I equal 1 to I equal 8, basically I is the node, we come up with 8 equations, and those create a tridiagonal matrix defined in terms of F, E, and G, and R. F, E, and G are defined in terms of the x's of those data points, and R is defined in terms of the y's of those data points. So I already can calculate the A matrix and the B vector here to get the unknowns, which are the 8 second derivatives that I'm after, right? So actually, now let's go through the code. So you can find that I actually created a vector for x and y for these 2 points, and we have 10 points. Now I created also a vector for E, G, R, and F that we have here, and you can find that they range from 1 to 8, because we have 8 equations here, 1 for each node. Here is one for the second derivative, vector for the second derivative, and we have 10 derivative, right? We have 8 for the interior ones, and we also have a derivative at the endpoints. And the derivative at the second derivative at the endpoint is initialized here, okay? And n is defined as the number of intervals, and in this case we have 9, and this is going to become clear as we go through the code. This is a very simple code of just inputting those values that I have here. So let's go through a brief outline of what the code is going to be about. So the first thing I want to do is I want to create my tridiagonal matrix. And what I mean by that is I want to create this A matrix here and the B vector. After that, we're going to apply the algorithm that I've explained before, which is the Thomas algorithm that deals with this type of matrix when we have so many zeros involved. Now that we have solved this, I have all the 8 second derivatives. So now we can actually go in and interpolate. Now we can actually find, okay, I want to know what it is at 16, what the temperature is at 16. What this interpolation code does, it finds this interval that I'm interested in, which is basically 14.2 and 19, and creates this equation for it, evaluates 16 in it, and gives me the corresponding temperature. And also with an added bonus, it creates also the first derivative and it creates also the second derivative. So let's actually go into more detail in terms of the code. So in creating the tridiagonal matrix, we see that there's a pattern here. For the first, we only have F1, G1, and R1, but from the second all the way to the 7th, we have E, F, and G available, right? But also for the 8th, we only have E and F. So I'm gonna calculate the first row on its own, the last row on its own, and I'm gonna loop from the 2nd to the 7th. So here, this is the code for the F1, G1, and R1. And you can see, I didn't want to confuse you, but here R is twice because the first one does this first part of R, and the second one just adds the second one to it. So if you prefer, you can actually make this into just one line of code if that would make it simpler. Down here, you can find that also E, F, and R so E8 and F8 and R8. And this is defined in terms of N just for the sake of making this code more general. So this is going to be 9 minus 1, so E8, F8, and R8. And this loop is from 2 to 9 minus 2, so 2 to 7, and that creates, again, all the way from E2 to E7, and F2 to F7, G2 to G7, and R2 to R7. So this code creates the tridiagonal matrix for us. So now, given that we have the tridiagonal matrix, basically the coefficient matrix A or the vector B that we're used to from solving systems of equations, now we can put in the Thomas algorithm, which is basically, this is the code for solving a system of equations that has a tridiagonal pattern to it. So this is a more efficient code, like I've described before, than doing a Gauss elimination or LU decomposition, because there's going to be unnecessary calculations if we use these techniques. So at this point, I have all the second derivatives, right? The second derivative at the first node all the way to the 8th node. So now we go into the interpolation code, and this is a very simple code. So the first thing that I would do is, this is an F statement that first tries to find where my point of interest is. So here my point of interest is 16. So I have a code up here that says XU, which is my point of interest, is in this cell. So it's going to take this 16 and it's going to go in here. And now it's going to ask, is 16 between xi minus 1 or is 16 between xi? And basically, if I is equal to 1, so this is x0 and x1. So it's going to ask, is 16 between 0 and 2.4? So the answer is no. It's going to go back. Is 16 between 2.4 and 5.1? If the answer is no, it goes back. Is it between 5.1 and 9.5? Is it between 9.5 and 14.2? And it's going to go another loop. Is it between 14.2 and 19? And the answer is yes. And now it's going to go into the code. So the code first, C1, C2, and C3, and C4. C stands for coefficient. So first I'm going to calculate this one in red. So this is what this code is doing. Calculates this one in red, then it calculates this one, then it calculates this one, and this is C4. So this is C1, C2, C3, and C4. Given that I calculated this, now I multiply it by this one. So T1 is multiplying it by this, but I want you to notice something. This is xi minus x. So this x is going to be your xu, or again, your point of interest. So you can see here is xi multiplied by, this is xu. This is my point of interest. And this is, T2 is going to be just C2 multiplied by this. T3 is going to be this C3 multiplied by this. And T4 is going to be C4 multiplied by this. And YU, which is basically the temperature I'm after, the temperature as this at this point of interest, which is 16, is just going to be T1 plus T2 plus T3 plus T4. So you find that this is very, very simple. That the idea here is just find the interval that you're in, create those 4 coefficients, multiplying by these, and you can also do this in just one line of code. But just for simplicity, I thought I would break them apart. Now, I went a step ahead and went ahead and created the first derivative. And just the first derivative is just T1. Basically, I got the T1 is a derivative of this first part here. T2 is the derivative of this second part, derivative of this, and derivative of that. Added all of them up, and this is the first derivative. Now in the second derivative, when you're going to do it, you're going to find that these two drop out, and I only have T1 and T2. And adding both of these evaluated at our point of interest is going to give us our second derivative at that point of interest. Now flag is equal to 1. The reason I have flag is equal to 1 is because, say for instance, I found my interval, I went in, I said flag is equal to 1. I have another F statement here. I'm saying if I is equal to n plus 1, which means 9 plus 1, 10. In other words, if I reached my last point, or if flag is equal to 1, in other words, I found my interval and I did my necessary calculations, then exit the loop or exit the do while loop. I have to put this kind of condition to get out of the loop, or I risk getting caught up in an infinite loop. So this is the condition that I'm giving it to get out of the do while loop. If it reached the last point that I have, or if flag is equal to 1, which means it found my interval and I did the necessary calculations. So yeah, and this is just a code that displays the y here and the first derivative and second derivative here. So let's recap quickly. So the first thing I do is I defined all the vectors that I'm dealing with. I was dealing with the x and y vectors, which are the data points that I have. This is E, G, R, and F. Those are used to create your tridiagonal matrix, right? And this is your vector to house all of your second derivatives. Basically, these are going to be the solutions of that tridiagonal matrix. And this is just for the factor. This is a vector when you're solving the system of equation. Here we initialized the second derivative at the first point and the last point as 0 as per the conditions. And this is the point that I'm interested in, and I'm telling it to draw it from this cell that we have here. The first thing that we do is we input all the values, then we create the tridiagonal matrix, right? We see that we have 3 parts here. The first part here is to get the information in the first row, second part from 2 to 7, third part is for the information in the 8th row. This is the Thomas algorithm, which is a system of equation solving technique specifically for tridiagonal, or it's an inefficient way of doing it by not dealing or doing unnecessary calculations. So given that we have that, we basically created all our second derivatives. So then we go into the interpolation. The F statement finds the interval that my point of interest is in this case is 16. Then it goes in, calculates the S1, S2, S3, and S4, those coefficients. Then it goes in, creates T1 to T4, which is basically multiplying by those x's. And this is an added bonus of getting the first derivative and the second derivative as well. We also have a condition here that breaks out of the do-while loop. It's either we reached the last point that we have, or a flag is equal to 1, which means that I found my interval and did the necessary calculations. So let's actually go ahead and I'm going to delete this. Go ahead and run the code. So if I run the code, so we can see at the depth of 16, we have 13.69 Celsius for our temperature. So let's actually go in, and at the depths of 16, and I go here, depths of 16, which is here. So I'm around 14 or 13.7 here. So you can see that it actually interpolated that. So we can actually try something else. We can try depth of 20, and if I run that, depth of 20, so I have a temperature of 12.7. So at depth of 20 here, I have here, you can see it's 12.7. So at the depth of 20, basically it found this interval, which is basically between 19 and 23, created this equation for it, and evaluated 20 using this equation, which ended up giving us 12.76 in this case, and also the first and second derivative. So up to this point, now you know how to do curve fitting, right? So you know how to do it through regression analysis, whether you're dealing with a polynomial or you're dealing with other types of more complex equations. And now you can actually use cubic spline to do interpolation, right? So this will mark the end of this lesson, and I will see you in future lessons.